So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are literally, um, wait a second, like, you know, if you have watched some of my most recent videos, so don't just take a look around that, just take a look on here, don't see that. We have proved the Ramanujan's paradox that says the sum of natural numbers, which is 1 plus 2 plus 3 plus 4 plus 5, and that just keeps going up to infinity, evaluates to negative 1 over 12. Like, we have talked about the things, the two important things that is violating here, actually violating, I would say, or maybe violated. So yeah, now just take a look at this. This is the sum as n goes from 1 to infinity of Riemann zeta of 2n over n times 2 to the 2n, and that is being evaluated to negative ln2. Like, we have talked about even we have generalized the Riemann zeta of 2n, right, in one of my earlier videos. Well, I'll paste the link of that in the description box of this video, right? You can watch that video, and that's really interesting. But if we sum this Riemann zeta of 2n as n is going from 1 to infinity, and let's divide the sum of that Riemann zeta over n times 2 to the 2n. So basically this sum is representing, let me just show you, it's Riemann zeta of 2 over 1 times 2 to the 2, which is 2 to the 2, plus Riemann zeta of 4 over n is 2, and it's 2 to the 2, and which is 2 to the 4, plus Riemann zeta of 6 over it's 3 and 2 to the 6, like literally. And then just take a look at this, the beauty of the sum. Riemann zeta of 8 over 4, 2 to the 8, and plus this is just going up to infinity. And the sum of this infinite sum is being evaluated to negative ln2. Like, can you imagine that? Can you just take a look at the beauty of this? Literally amazing, mind-blowing, incredible, right? And yeah, we are just going to prove this down using the result that we have talked about. We have proved in one of my earlier videos, and I'll paste the link of that video in the description box, like the link of that video in the description box of this video. Don't worry about that. And the thing that we are going to begin our journey from is the infinite sum representation of cotangent function in terms of, actually I think I have proven this in the video in which I have generalized this Riemann zeta of 2n. Well, I'll just take a look at that, and I'll paste the link. If I have made an individual video on that, like the thing that I'm just going to write over here, I'll paste the link of that video. But if I haven't, but I'm sure that I have talked about that thing in one of videos, so most probably it's the video in which I have generalized this, right? So it's pi z cotangent of pi z equals 1 minus 2 times the sum as n goes from 1 to infinity of Riemann zeta of 2n. Actually, this Riemann zeta is crazy. No, it's fine. But and z to the 2n. So this thing we have proven. We have proved. Yeah. Isn't it amazing? And with the help of this one, actually, we are just going to use some basic manipulations. Don't worry, I'm not going to like use some higher mathematics to prove this down, but some basic things like integrals, and that too in basic integrals though. So don't worry about that. So we have that equation, right? So we are having pi z cotangent pi z equals 1 minus 2, the sum as n goes from 1 to infinity of Riemann zeta of 2n z to the 2n. Now isolating this sum, so isolating this is gonna give us equals 1 over 2 minus 1 over 2 pi z cotangent pi z. And then our next step is dividing both sides with z actually. So z and z. So that it's gonna be the sum as n goes from 1 to infinity of Riemann zeta of 2n z to the 2n minus 1, right? Because that's gonna be like basics of exponential rules. And it's gonna be 1 over 2z and minus this z and this z will cancel out, and we would be left with pi over 2 cotangent pi over c. Right, okay, so far we have got to reach up to here. And now our next step is gonna be integrating both sides with respect to z. Okay, let's do that either. It's not gonna take a lot of time though. Okay, so integral the sum as n goes from 1 to infinity of Riemann zeta of 2n z to the 2n minus 1 dz equals 1 over actually 2z minus it's pi over 2 cotangent pi z and dz, right? Since the sum and the integral due to linearity, we can just switch up the order of them. And again, the Riemann zeta of 2n would be treated as a constant if we are integrating with respect to z. So basically this is the sum as n goes from 1 to infinity of Riemann zeta of 2n integral of z to the 2n minus 1 dz. We have talked about the proof of this integral equals, and the integral of 1 over z is ln z. So 1 over 2 ln z, and the integral of cotangent of pi z is pi over 2 1 over pi ln sine pi z. Okay, wait a second. I have just integrated without explaining it to you. And now you would ask me, Aman, you cannot do that. So let me just see. Yeah, it is covering far here. So we know that the integral of 1 over z is ln z actually with respect to dz actually, right? And if we talk about the integral of cotangent pi z, so cotangent pi z can be written as integral cosine pi z over sine pi z, right? And we know that the derivative of sine pi z is like the derivative of sine is cosine, right? So that's gonna be like it's a basic integral. If you're having the derivative f of f dash x over f of x dx, it's gonna be ln of f of x, right? So it's the basics, and you know about that. It's just u sub, but with a factor of 1 over pi, because when you plug pi z equals m, so dz is gonna be dm over pi, so this factor is here, and we are having ln of this denominator sine of pi z. That's it. So I hope you are done with this and you don't need extra attention to these things. Okay, and that is what we have done in like here, right? And if we talk about this integral, so that is just z to the 2n over 2n, right? Wow. So it is the sum as n goes from 1 to infinity of Riemann zeta of 2n, and it's z to the 2n over 2n equals, we can factor 1 over 2 from this, so it's ln z, and minus this pi and pi cancels out successfully, it's ln sine pi z. So this 2 and this factor 2 are cancelling out with each other, and finally we are having this sum as n goes from 1 to infinity of yeah, now it sounds good. Riemann zeta of 2n is z to the 2n over n equals ln z over sine pi z. Well, how did I combine that? It's the rules and the formulas of natural logarithms. Okay, so now, like we were we were just talking about something which evaluates to negative ln 2, right? So now let's talk about that. So that's the generalized form actually of the one we were looking for actually, right? So basically, since we cannot plug z equals 1 here because it's gonna be sine pi, so it's 0, and the argument of ln is gonna be infinity or maybe tending to infinity, so that's not cool at all, right? So for that case, we have to plug z equals 1 over 2, right? So when you plug z equals 1 over 2, so it's gonna be sine pi over 2, right? And sine pi over 2 is 1. So we would be just getting rid of this term, right? And let's talk about the right hand side. So when you plug n equals 1 to infinity of Riemann zeta of 2n, when you plug z equals 1 over 2, so that's gonna be 1 over 2 to the 2n. So basically it's n times 2 to the 2n, right? The one we were looking for, and it's ln 1 over 2 over 1, so that's gonna be ln of 1 over 2, and ln of 1 over 2 is negative ln 2. Hence we have done it, guys. What, like, just take a look at this thing. It was beauty. We have done it easily, and I don't think that we did it overwhelming or anything like that. Yeah, it was quite good, and yeah, it was easy. It was literally easy. But the thing that you need to know about the relation between the sum of like Riemann zetas of even arguments and the cotangent function, right? So with the help of that, we just got this beautiful and incredible result of that infinite sum. Yeah, guys. Again, guys, if you got to learn something from this video, make sure to like, subscribe, and share. And it's fine. And if you have any kind of doubts so far, you can ask me in the comment section. You are free to ask me in the comment section. You should definitely ask me in the comment section. And again, if you have any kind of oh wait a second, I have already told that to you. So yeah, goodbye guys, take care, love you, and be careful. And yeah, goodbye. Let's meet you let's just talk about ourselves and about mathematics in the next video. Goodbye guys.